Hello and welcome back to College Algebra, MAT 150. In this lecture, we will be discussing combined transformations to graphs. So, in the previous sections, we learned about the types of transformations we have. It was first talked about shifts, then reflections, and then we talked about stretches and shrinks. Well, unsurprisingly, they're all kind of three working together, and we can do all three at the same time. We don't have to do one or the other. And here we actually have the order that we're supposed to do them for various reasons. One is the first is to do stretches or shrinks. Then it says to do all reflections, find all reflections, and then do shifts. To be honest, you can actually sort of combine the first two, but you always do want to save shifts for last. So you can do reflections and stretches kind of together at the same time if you really want, but you really should do shifts last. So what is actually going on when we're doing these transformations? Well, here I have a sort of a list of what's going on to each point when you do this. So if you're shifting up, again, we're assuming by k, so it's AB and then add k. We're shifting down, we're subtracting k, and this is where it gets interesting. If you're shifting left or right, you're actually doing the opposite. You're subtracting, so here we were adding k to the y coordinate, here we're going to be subtracting k, and we're shifting to the right, here we're going to be adding k. So again, you know this from when it's exactly the opposite sign. When you see this, that's what you do. So if you see a plus k on the inside of the function, then you're going to be subtracting it on the point or shifting left. Reflections, just multiply whatever coordinate by y. Here it's the x coordinate, so we're flipping over the x-axis, which is verticality, so we should be reflecting, so we should be negating the y coordinates of our graphs, of points on our graph. And for about the y-axis, that's left to right, so we negate the x-coordinate of our points on our graph. And then vertical stretches, again, we saw what happened here. We just multiplied by the factor to the y-coordinate. But again, when you're dealing with with stuff that's horizontal stuff on the inside of the function, it's backwards from what you would think. So if you're multiplying by k, to find the new point, you actually divide by k, and you do it to the x-coordinate. Versus here, the vertical stuff you do to the y-coordinate. All right, so let's look at this first one. And here, notice we have a couple of graphs. Maybe you might want to do a couple of iterations. So let's look at the base graph. Let's start there. That's usually a great place to start, which is x squared. 0, 0, 1, 1, negative 1, 1. I'm going to stop writing the base points every single time. And what are we doing here? Well, something kind of like this. Not a perfect graph. Trying to make it a little bit better here. But it doesn't have to be. Again, this is also just the sketch for everything we're going to do. Well, what are we going to do? If we follow the rules, we're going to start with stretches. Then we're going to deal with reflections. So the stretches, we're going to multiply our y's by 2, okay? Because that's the vertical stretch. So it's a vertical stretch by 2. It's oftentimes a good idea to at least list what's going on because there could be a couple of things. So we have that. We also have an x-axis reflection because of the negative which is on the outside. So we're going to start with the vertical stretch of 2. So multiply this by 2. So this instead of 1, 1 and negative 1, 1, it's going to become 0, 0, 1, 2, and negative 1, 2. Something like this. And then we're going, so we did that part. And now for the next part, we're going to reflect it over the x-axis, so up and down. So we're going to still have 0, 0. What this does, again, mathematically, is you're negating the y values, or the y coordinates. So you get, instead of this, 0, 0, we have 1, negative 2, and negative 1, negative 2. And then this is our graph, the graph of f. And what is the range? How far down does it start? Negative infinity. How far up does it go? It goes to 1. Or it goes to 0, excuse me. All right. Let's take a look at this next one. G of x is given by x plus 1 quantity cubed, then we subtract 3. So what is the base graph? The base graph is x cubed. Again, what is the main thing? Do you see a square root? Do you see an absolute value? Do you see what power do you see it to? So on and so forth. And by the way, for these transformations, all we're really doing is we're doing one at a time. So stuff that has a bunch of stuff going on, we're not focused on those. And we never will in this class. Okay? In that case, just whip out a calculator or find some graphing utility and plug it in there and find out what it looks like. But x cubed, the base graph, we go 1, 1, 0, 0, negative 1, negative 1. And then, so sort of a half parabola up, sort of a half parabola down. Maybe give it more parabola look there. But this is our base graph. And then this plus 1 and this minus 3 means it goes left 1, and minus on the outside is down 3. So 0, 0, left 1, down 3. Left 1, down 3 gives us this. And again, this is a good idea of where to use the base points. So we went right 1, up 1, and left 1, down 1. Right 1, up 1, left 1, down 1. All right, and this is the graph of G. We also want to talk about the range of G and what happens in this particular case. Well, how far does it go down? Negative infinity. How far does it go up? Well, we got an arrow that points up forever, so positive infinity. One more. So in this case, h of x is given by negative 2 times the absolute value of x minus 6. So we have b of x is the absolute value of x, which is just the v. Perfect diagonal, perfect diagonal. Quite perfect, but you get the idea. And then, so we have these base points, 0, 0, 1, 1, negative 1, 1. And we, first we see, let's note all the transformations. So we got multiplying by 2, so vertical stretch by 2. So v stretch by 2. We're also doing a negative on the outside, so x-axis reflection. And then what else are we doing? We're going right 6. So minus 6 on the inside is right 6. So again, I've mentioned this before, we can sort of combine reflections and stretches. And in this case, since both of these are applying to the y, we can do that. So it's really negative 2 is being multiplied by the y, so it's stretching it, so vertically, so to 2, and then it's reflecting it. So instead of 1, 1, we're taking the y value here of 1 and multiplying by negative 2, so it becomes 1, negative 2. And similarly, on the other side, we get negative 1, negative 2. And we get something like this. And now we still have to go right 6. So we're going to take this and go right 6. 1, 2, 3, 4, 5. Uh-oh, we didn't leave enough space here. 6. So let's label this just to be clear. 2, 4, 6. And there's still one more mark we need to make, because here at 0, 0, or here at 6, 0, excuse me, we go left 1, down 2, use the base points, left 1, down 2, and right 1, down 2. And especially now, since we're outside of the grid, we really, really, really want to label our points. I've been neglecting that, but we're going to do that here especially. So this point is 7, negative 2. This is 5, so at the 5 mark, negative 2. And just to be extra clear, this is 6, 0. And I probably shouldn't have put a line here, but I guess I was trying to continue on the grid, but yeah. So this is our graph right here. We have H is our graph. And what's the range of H? How far down does it start? Maybe we should make more room for this. The range of H. How far down? Negative infinity. How far up does it go? It goes to 0. The bracket. All right, so that concludes the graphs with them being combined. But with the combined transformations, we can also talk about points. So if we don't know what the actual function is, and I said you plug in 1, you get out 3 for this function, so f of 1 equals 3 is what we're saying. And then we did transformations, so we multiplied by 3, and we did negative x. We had 3 times f of negative x. What would be a point that we could get out? Well, using transformation, so what do we see here? Well, we have a vertical stretch. It's a stretch by 3. And we also have on the inside the negative, so it's a y-axis reflection. So we're going to take the point 1, 3, and the vertical stretch is going to affect the y value. So we're going to multiply the y value by 3. So this becomes 1, 9. And then the y-axis reflection, again, that affects, again, left and right. So that affects the x. So we negate x. And we get negative 1, 9 as our answer. And then if you don't believe this, you can check your work. Does this make sense? We said that f, what does 1, 3 being a point on f mean? It means if you plug in 1, you get out 3. Right? So let's see if this happens. Well, for this function. So we're trying to say h of negative 1 equals 9. Well, h of negative 1 is 3 times f of negative of x. But in this case, we plugged in negative 1 for our x. Negative of negative 1 is equal to 1. And what did we say f of 1 was? It was 3. So we get 3 times 3, which is in fact 9. So if you plug in negative 1, you get out 9. That's exactly what we're saying by those transformations. So we can kind of verify it. So let's do the same thing again. 2, negative 2 is a point of g of x. And then if we have transformations to get a new function, what would we have? Well, what are the transformations? We have a negative on the outside, so it's an x-axis reflection. And so it affects verticality. We also have the plus 2 on the inside, so it goes left 2. And then we have plus 4 on the outside, so that's up 4. So let's take our points, or take our single point rather, and then do that. So x-axis reflection deals with verticality, so we're actually multiplying the y's by a negative. So instead of 2, negative 2, it becomes 2, 2. We go left 2, that means we're taking the x values and we're subtracting 2. So we're dealing with the x value, so what is 2 minus 2? That's 0, 2. And then up 4 deals with the y values, so we're taking the y values and we're adding 4. So what is 4 plus 2? That's 6. 0, 6. And this is our answer. We can confirm though by making sure that what does this point actually say? It says if you plug in 2, you're going to get out negative 2. So if we can confirm this using this idea. K of 0 equals negative of g of 0 plus 2 plus 4. And 0 plus 2 is 2. So negative g of 2 plus 4. G of 2, as we noted, is negative 2, so negative of negative 2. Negative of negative is positive, so 2 plus 4, which is in fact 6. So we plug in 0 to k and we get out 6, which is exactly what this says. This concludes this lecture.